Everyone, welcome to the video lecture for Unit 2, Module 4.4, which is the final video lecture in Module 4. We're going to talk about cardiodynamics here. As always, here are your learning objectives. Let's go ahead and get started. So the term cardiodynamics refers to the movements and forces generated during the cardiac contractions. Each time the heart beats, the two ventricles eject equal amounts of blood. Earlier we introduced these terms, the end diastolic volume, which is the amount of blood in each ventricle at the end of the ventricular diastole, or the start of ventricular systole, end systolic volume, which is the amount of blood remaining in each ventricle at the end of the ventricular systole, or the start of ventricular diastole, the stroke volume, which is the amount of blood pumped out of each ventricle during a single beat, and it can be expressed as stroke volume is equal to EDV minus ESV, and ejection fraction, which is the percentage of the EDV represented by the SV. Stroke volume is the most important factor in an examination of a single cardiac cycle. If the heart were a simple hand pump, the stroke volume would be the amount of water pumped in one up-down cycle of the handle. Where you stop when you lift the handle determines how much water the pump contains, the end diastolic volume. How far you push the handle down determines how much water remains in the pump at the end of the cycle, or the end systolic volume. You pump the maximum amount of water when you pull the handle all the way to the top and then push it all the way to the bottom. In other words, you get the largest stroke volume when the EDV is as large as it can be and the ESV is as small as it can be. When considering cardiac function over time, physicians generally are most interested in the cardiac output, which is the amount of blood pumped by the left ventricle in 1 minute. In essence, the cardiac output is an indication of the blood flow to the peripheral tissues, and without adequate blood flow, homeostasis cannot be maintained. The cardiac output provides a useful indication of ventricular efficiency over time. We can calculate it by multiplying the heart rate by the average stroke volume. The body precisely adjusts cardiac output to supply peripheral tissues with enough blood as conditions change. When necessary, the heart rate can increase by 250%, and the stroke volume in a normal heart can almost double. So just a brief overview. There are factors affecting cardiac output can be adjusted by change in either heart rate or stroke volume. For convenience, we'll consider these independently as we discuss the individual factors involved. However, changes in cardiac output generally reflect changes in both heart rate and stroke volume. The heart rate can be adjusted by the activities of the autonomic nervous system or by circulating hormones. The stroke volume can be adjusted by change in the end diastolic volume, or how full a ventricle is when it starts to contract, the end systolic volume, how much blood remains in a ventricle after it contracts, or both. There are some factors here affecting the heart rate. Under normal circumstances, autonomic activity and circulating hormones make homeostatic adjustments to the heart rate as cardiovascular demands change. These factors affect modifying the natural rhythm of the heart. Even a heart removed for a heart transplant continues to beat unless it's kept chilled in a preservation solution. The sympathetic and parasympathetic divisions of the autonomic nervous system innervate the heart by means of the nerve network known as the cardiac plexus. Postganglionic sympathetic neurons are located in the cervical and upper thoracic ganglia. The vagus nerve, or nerve 10, carries parasympathetic preganglionic fibers to small ganglia in the cardiac plexus. Both A and S divisions innervate the SA and AV nodes and the atrial muscle cells. Both divisions also innervate ventricular muscle cells, but sympathetic muscle fibers far outnumber parasympathetic fibers there. The cardiac centers of the medulla oblongata contain the autonomic headquarters for cardiac control. The cardioacceleratory center controls sympathetic neurons that increase the heart rate. The adjacent cardioinhibitory center controls the parasympathetic neurons that slow the heart rate. Reflex pathways regulate the cardiac centers. They also receive input from higher centers, especially from the parasympathetic and sympathetic headquarters and the hypothalamus. Information about the status of the cardiovascular system arise over visceral sensory fibers accompanying the vagus nerve and the sympathetic nerves of the cardiac plexus. The cardiac centers monitor baroreceptors and chemoreceptors innervated by the glossopharyngeal, or nerve 9, and vagus nerves, or nerve 10. On the basis of the information received, the cardiac centers adjust the heart's activity to maintain adequate circulation to vital organs, such as the brain. The cardiac centers respond to changes in blood pressure, as reported by baroreceptors, and changes in arterial concentration of dissolved oxygen and carbon dioxide, as reported by chemoreceptors. For example, a decline in blood pressure or oxygen concentrations, or an increase in carbon dioxide levels, generally means that the heart must work harder to meet the demands of peripheral tissues. The cardiac centers then call for an increase in cardiac activity. So let's consider autonomic tone for a minute. Like other organs with dual innervation, the heart has a resting autonomic tone. Both autonomic divisions are normally active at a steady background level. releasing ACH and norepi at the nodes and into the myocardium. For this reason, cutting the vagus nerve increases the heart rate, and sympathetic blocking agents slow the heart rate. Parasympathetic effects dominate in a healthy resting individual. Without autonomic innervation, the pacemaker cells of the SA node establish the heart rate. Such heart beats at a rate of 80 to 100 beats per minute. At rest, a typical adult heart with normal innervation beats more slowly, about 70 to 80 beats per minute, due to activity in the parasympathetic nerves innervating the SA node. If parasympathetic activity increases, the heart rate declines further. Conversely, the heart rate increases if parasympathetic activity decreases, or if sympathetic activation occurs. Through dual innervation and adjustments in autonomic tone, the ANS can make very delicate adjustments in cardiovascular function to meet the demands of other systems. So how do sympathetic and parasympathetic divisions alter the heart rate? They do so by changing the ionic permeabilities of cells in the conducting system. The most dramatic effects take place at the SA node, which affects the heart rate through changes in the rate at which the impulses are generated. Consider the SA node of a resting individual whose heart is beating at 75 beats per minute. Any factor that changes the rate of spontaneous depolarization or the duration of repolarization in nodal cells will alter the heart rate by changing the time required for these cells to reach threshold. Acetylcholine released by the parasympathetic neurons opens chemically jaded potassium channels in the plasma membrane. Then potassium leaves the nodal cells, dramatically slowing their rate of spontaneous depolarization, also slightly extending the duration of repolarization. As a result, heart rate declines. Norepi released by sympathetic neurons binds to beta-1 receptors, leading to the opening of sodium ion channels and calcium ion channels. Then an influx of positively charged ion increases the rate of depolarization and shortens the period of repolarization. The nodal cells reach threshold more quickly, and the heart rate increases. The atrial reflex, or the brain bridge reflex, involves adjustments in the heart rate in response to an increase in the venous return, or the amount of blood returning to the heart through the veins. When the walls of the right atrium are stretched, stretch receptors there trigger a reflexive increase in heart rate by stimulating sympathetic activity. Thus, when the rate of venous return to the heart rate increases, so does the heart rate. And for this reason, the cardiac output increases as well. Epinephrine, norepinephrine, and thyroid hormone increase heart rate by their effect on the SA node. The effects of epinephrine on the SA node are similar to those of norepi. Epi also affects the contractile cells. After massive sympathetic stimulation of the adrenal medullae, the myocardium may become so excitable that abnormal contractions occur. In addition to its indirect effect on heart rate by the atrial reflex, venous return also directly affects nodal cells. When the venous return increases, the atria receive more blood and the walls are stretched. Stretching of the cardiac muscle fibers of the SA node leads to more rapid depolarization and an increase in the heart rate. The stroke volume is the difference between the end diastolic volume and the end systolic volume. Changes in either EDV or ESV can change the stroke volume and thus cardiac output. The factors involved in regulation of stroke volume are indicated. Recall that the EDV is the amount of blood in a ventricle at the time of the end of diastole, just before contraction begins. Two factors affect this volume: the filling time and the venous return. Filling time is the duration of ventricular diastole. It depends entirely on the heart rate. The faster the heart rate, the shorter is the time available for filling. Venous return is variable over this period. It varies in response to changes in cardiac output, blood volume, patterns of peripheral circulation, skeletal muscle activity, and other factors that affect the rate of blood flow back to the heart. The degree of stretching in ventricular muscle cells during ventricular diastole is called the preload. The preload is directly proportional to the EDV. The greater the EDV, the larger the preload. Preload matters because it affects the ability of the muscle cells to produce tension. As sarcomere length increases past resting length, the amount of force produced during systole increases. The amount of preload, and hence the degree of myocardial stretching, varies with the demands on the heart. When you are standing at rest, your EDV is low. The ventricular muscle is stretched very little, and the sarcomeres are relatively short. During ventricular systole, the cardiac muscle cells develop little power, and the ESV, or the amount of blood in the ventricle after contraction, is relatively high because the muscle cells contracted only a short distance. If you begin exercising, venous return increases and more blood flows into your heart. Your EDV increases, and the myocardium stretches further. As the sarcomeres approach optimal lengths, the ventricular muscle cells can contract more efficiently and produce more forceful contractions. They also shorten more, and the blood is pumped out of your heart. In general, the greater the EDV, the larger the stroke volume. Stretching the cardiac muscle cells past their optimum length would reduce the force of contraction, but this degree of stretching does not normally take place. Myocardial connective tissues, the cardiac skeleton, and the pericardial sac all limit expansions of the ventricles. The relationship between the amount of ventricular stretching and the contractile force means that within normal physiological limits, increasing the EDV results in a corresponding increase in the stroke volume. This general rule of more in equals more out was first proposed by Ernest Starling, based on his studies and the research by Otto Frank. The relationship is known as the Frank-Starling principle, or Starling's law of the heart. Autonomic adjustments to cardiac output normally make the effects of the Frank-Starling principle difficult to see. However, we can see the effects more clearly in individuals who have received a heart transplant, because the implanted heart is not innervated by the ANS. The most obvious effect of the Frank-Starling principle in these hearts is that the outputs of the left and right ventricles remain balanced under a variety of conditions. Consider, for example, an individual at rest with the two ventricles ejecting equal volumes of blood. Although the ventricles contract together, they work in series. When the heart contracts, blood leaving the right ventricle heads to the lungs. During the next ventricular diastole, that volume of blood passes to the left atrium to be ejected by the left ventricle at the next contraction. If the venous return decreases, the EDV of the right ventricle will decline. During ventricular systole, the right ventricle then pumps less blood to the lungs. In the next cardiac cycle, the EDV of the left ventricle will be reduced, and the ventricle will eject a smaller volume of blood. The output of the two ventricles will again be in balance, but both will have smaller stroke volumes than they did initially. After the ventricle has contracted and ejected the stroke volume, the amount of blood that remains in the ventricle at the end of the ventricular systole is the ESV. Three factors that influence the ESV are the preload, which we talked about earlier, the contractility of the ventricle, and the afterload. Contractility is the amount of force produced during contraction at a given preload. Under normal circumstances, autonomic innervation or circulating hormones can alter contractility. Under special circumstances, drugs or abnormal ion concentrations in the extracellular fluid can alter contractility. Factors that increase contractility are said to have a positive ionotropic action. Factors that decrease contractility have a negative ionotropic action. Positive ionotropic agents typically stimulate calcium entry into the cardiac muscle cells, thus increasing the force and duration of ventricular contractions. Negative ionotropic action or agents may block calcium movement or depress cardiac muscle metabolism. Positive and negative ionotropic factors include ANS activity, hormones, and changes in extracellular ion concentrations. Autonomic activity alters the degree of contraction and changes the ESV in the following ways. Sympathetic stimulation has a positive ionotropic effect. It causes the release of norepi by postganglionic fibers of the cardiac nerves and the secretion of epi and norepi by the adrenal medullae. These hormones affect heart rate, as we discussed shortly. They also stimulate alpha and beta receptors in cardiac muscle plasma membranes. This stimulation increases cardiac muscle cell metabolism and the force and degree of contraction. The net effect is that the ventricles contract more forcefully, increasing the ejection fraction and decreasing the ESV. Parasympathetic stimulation from the vagus nerves has a negative ionotropic effect. The primary effect of acetylcholine is at the membrane surface, where it produces hyperpolarization and inhibition. As a result, the force of cardiac contractions is reduced. The atria show the greatest changes in contractile force because the ventricles are not extensively innervated by the parasympathetic division. However, under strong parasympathetic stimulation or after the administration of drugs that mimic the actions of ACH, the ventricles contract less forcefully and the ejection fraction decreases, and the ESV becomes larger. Many hormones affect the contractility of the heart. For example, epi, norepi, and thyroid hormones all have positive ionotropic effects. Glucagon has a positive ionotropic effect. Before synthetic ionotropic agents were available, glucagon was widely used to stimulate cardiac function. It's still used in cardiac emergencies and to treat some forms of heart disease. The drugs isoproterenol, dopamine, and dobutamine mimic the actions of epi and norepi by stimulating beta-1 receptors on the cardiac muscle cells. Dopamine at high doses and dobutamine also stimulate calcium entry through alpha-1 receptor stimulation. Digitalis and related drugs elevate intracellular calcium concentrations, but by a different mechanism. They interfere with the removal of calcium from the cytosol of cardiac muscle cells. Many drugs used to treat hypertension or high blood pressure have a negative ionotropic action. Beta-blocking drugs such as propranolol, timolol, metoprolol, atenolol, and labetalol block beta receptors, alpha receptors, or both, and prevent sympathetic stimulation of the heart. Calcium channel blockers such as nifedipine or verapamil have a negative ionotropic effect. The afterload is the amount of tension that the contracting ventricle must produce to force open the semilunar valve and eject blood. Afterload increases with the increased resistance to blood flow out of the ventricle. The greater the afterload, the stronger the period of isovolumeric contraction, the shorter the duration of ventricular ejection, and the larger the ESV. So in other words, as the afterload increases, The stroke volume decreases. Any factor that restricts blood flow to the atrial system increases afterload. For example, either the constriction of peripheral blood vessels or a circulatory blockage elevates arterial blood pressures and increases the afterload. If the afterload is too great, the ventricle cannot eject blood. Such a high afterload is rare in a normal heart. However, damage to the heart muscle can weaken the myocardium enough that even a modest rise in arterial blood pressure can reduce stroke volume to dangerously low levels, producing symptoms of heart failure. Damage to the semilunar valve that restricts blood flow will also increase afterload. This figure summarizes the factors that regulate the heart rate and the stroke volume, which interact to determine the cardiac output under normal conditions. The heart rate is influenced by the autonomic nervous system, circulating hormones, and the venous return. Let's just cover some facts that are presented in this figure. Sympathetic stimulation increases the heart rate, and parasympathetic stimulation decreases it. Under resting conditions, parasympathetic tone dominates, and the heart rate is slightly lower than the intrinsic heart rate. When activity levels rise, venous return increases and triggers the atrial reflex. The result is an increase in sympathetic tone and an increase in heart rate. Circulating hormones, specifically epi, norepi, and T3, accelerate heart rate. An increase in venous return stretches the nodal cells and increases the heart rate. The stroke volume is the difference between the end diastolic volume, or the EDV, and the end systolic volume, or the ESV. The EDV is determined by the available filling time and the rate of venous return. And finally, the ESV is determined by the amount of preload, or the degree of myocardial stretching, the degree of contractility, which is adjusted by hormones and autonomic innervation, and the afterload, or the atrial resistance to the blood flow out of the heart. In most healthy people, increasing both the stroke volume and the heart rate, such as what occurs during heavy exercise, can raise the cardiac output by 300 to 500% to about 18 to 30 liters per minute. The difference between resting and maximal cardiac outputs is the cardiac reserve. Trained athletes exercising at maximal levels may increase cardiac output by nearly 700% to about 40 liters per minute. Cardiac output cannot increase indefinitely, primarily because the available filling time shortens as the heart rate increases. At heart rates up to 160 to 180 beats per minute, the combination of increased rate of venous return and increased contractility compensates for the reduction in filling time. Over this range, cardiac output and heart rate increase together, but if the heart rate continues to climb, the stroke volume begins to drop. Cardiac output first plateaus and then declines.